Oh, I
Cool.
changed the voice.
Did it? Oh, it sounded the same for me. I must have not updated.
All right.
Um, Alrighty. Well, hi everyone. Great to see, I guess, new faces. And if you're watching this recording, hi. A little introduction. My name is John Tabakian. I was the X-Zone lead for 2 years. 2 years ago, last year, I was the ASME technical vice president. And today, I guess I'm going to be going over the code that I helped develop for Guardian last year. So I'm gonna try to do like a high level overview first, and then obviously we'll go in a little bit more detail, and I will try to answer as many questions as possible. I will be able to answer most questions about the legs, probably all, but stuff about like the vision stuff I can try to answer, but that's not exactly my area of expertise. But anyways, I guess let's go ahead and get started. So all of the code for the Guardian's legs is essentially in these 4 files. So we have legs demo, legs path, and kinematics. Legs demo is basically just a console that I just threw together really quickly. So it's just one big loop that checks in, takes in a command, and then it has a bunch of stuff. So like for example, you could type help and it tells you everything. So this isn't necessarily too complicated. We can circle back on this if anyone's interested, but this stuff is basically just user input stuff, and then it calls the appropriate function based on what you pass it and all that stuff. There's also a demo loop in here, just so that if you put I added a demo command where if you put demo it just has like a random, or not random, but like a pre-assigned motion loop. But like it's just a demo mode for like a toy. So that's also in here, but again, not really super important, but if anyone's interested, we can circle back. The main of everything is in this legs.py file. This is where most of the controls, if not all of the controls, happens. Path.py is mostly helper functions, minus this simulation code. I'm using Matlab, which is a Python package that basically gives you MATLAB plot commands. It's very convenient and very useful for making quick animations, especially if you know how to do that stuff in MATLAB. So, not a perfect method, but I was certainly way more comfortable in MATLAB than Python when I did this, so hence why I did that. But so I have a simulation code in here, but besides that, you can see the rest of it is all helper functions, and we'll go through all that stuff as well. Lastly, we have kinematics.py. This is a very short file as well. It's excuse me, 2 main helper functions, only one of which we ended up using. And if you've taken kinematics courses, so the 163 A, B, and C series, this might make sense to you. If not, I'll try to give a quick intro, but without diving into too much of that. So yeah, that's basically the structure. Any questions on just like the structure of how the code is? So this is completely independent for the legs. So unfortunately, it wasn't interfaced with the rest of the stuff Guardian does, like the vision and stuff. But it shouldn't be too difficult because I have everything in like callable form, if like callable functions. So we can talk about that in a bit. But in terms of just general structure for this stuff, any questions at all? Cool. All right, so getting started, legs has 2 classes. We have a class called Guardian, and then we have our class called Leg. I'm assuming everyone here is familiar with Guardian, right? At least like in some aspect what that robot looks like, what the purpose is. So Guardian has 6 legs. So similarly, our Guardian class has an array of 6 leg class objects. I'm using NumPy, which is another Python package that lets you do a lot of matrix math. It's very convenient. It basically overhauls the way arrays are handled in Python. It's very convenient for math and that kind of stuff. So yeah, going through Guardian, we'll go through the initialization first. So you can see it takes in a zeta. This is just so in kinematics of robotics, you'll learn if you take that course, and if you don't, it's still interesting in my opinion. For 2D robotics, which we treated Guardian as a 2D robot, so think of it like a car, less of like a six-legged spider thing, or I guess not spider because that's 8. But anyways, so for 2D kinematics, you can describe the location of an object with 3 numbers. You have your x position, your y position, and your theta, your angle, right? And that will tell you basically where your robot is in 2D space, because in the case of Guardian, we didn't really care about going up and down as much. So zeta here is just my x, y, and theta, and that's just tracking, where my Guardian is. Obviously, it's a variable for my init. That's just because in case you wanted to, start off the robot somewhere else, you can kind of overwrite the 000 and say, hey, by the way, Guardian's starting position is actually here. Next, we have DH. This is your DH parameters, basically for kinematics of robotics. Again, just going back to that class, any manipulator, so like a robotic arm, right? You can describe using what's called DH parameters. Basically, fancy math way of saying we're assigning like length and rotation values, all this kind of stuff. You're basically parameterizing robotic arms. So the math isn't too relevant if you could just like follow me with that concept of it's just a fancy way of modeling my arm in math, right? Hopefully that makes sense. And then by extension, I am modeling each leg as an arm. So that's why this is present here. So basically, instead of one, arm like you'd find in a factory, we have 6 of them and they're all attached to the same base. Doesn't change the math. So that's where DH is. It's taken in by default as empty. And then it's auto assigned if you don't pre-assign it. I did it this way because I was getting some weird errors with the NumPy if I tried to define this in here, but it ultimately changes nothing. It's just the same thing as Zeta. It has a default value right here, or you can initialize something else. Lastly, path offset, or I guess this is just sampling time. This is more or less just like from a controls perspective, how quickly we're sampling, move, stuff like that. If you had a sensor, it would also do that. In this case, there is no sensor, but the idea is still there of every 0.1 milliseconds, I believe this is in. Either way, whatever that the unit is, I can tell looking at the rest of the code. That will, every that often of time increment, we look and what we have to do. So that's just that is path offset. I'm going to come back to this one. Essentially, this is what allows the robot to walk correctly. And so I kind of have to explain how the walking works before I come back to that. So just know that same thing. It's a default value, but we can, I have you can initialize it, override it if you wanted to. Self.legs, here's my array of leg objects. Self.zeta, again, all this stuff is just default initialization. Self.current position. This is actually current position in what will be defined as your path array. So essentially, the way the movement works, and I'm going to hop over the path class now that this will make sense. There is a okay. I guess I gotta back up one more second real quick. Let me open up Paint. Hopefully this loads. I was having problems with this earlier. Okay. So the way Guardian walks, and I won't take too long on this because obviously I don't want to get too specific. So 6-sided. So here's my Guardian, right? I have my 6 legs. The way Guardian walks is we assign basically a path in, let me change the color real quick, a path in this plane to each arm or to each leg. And all these planes are parallel, right? Because we want the robot to walk in the same direction, in this case, this way. So the way this looks is if I were to, this is the plane. So if I were to take this normal, right? What we're drawing out is this semicircle. And what the leg is doing is it's going, okay, I'm going to move where my leg tip is along this circle. And then by doing that, I'm walking, right? Does that make sense? And so that's how the walking works. There's 6 legs. Each leg has the same semicircle. And what happens is each leg is just delayed. So for example, if I erase these, we'll have this leg is right here while this leg is here, for example, while this leg is here. All 3 have the same path, but by delaying the path that the leg is following, we get proper walking animation. So that's in a nutshell. I'll circle back to this if you guys are interested. I'll be happy to talk about it. But for the sake of the rest of the code, that's what this is. This really long array. This is my path for forward motion, so path F. This is my path for counterclockwise rotation. And all it is, like I said, this is just your array of X, Y, Z points that make that path that our robot is, that our leg is walking. So for the forward path, you can see our Z value and our X value is changing. Our Y values are constant. That makes sense because, like I said, all these planes are, parallel to each other. In this case, this is, that's a terrible color for this. This is X, this is Y, Z is out of the page. So you can see here, all my Y values are the same. Z is changing, obviously, because that's what's going up and down. And then my X is, this front and back motion, hence why it's going from negative to positive. For counterclockwise, obviously, all 3 have to change, and that's because the leg has to do like a curved arc, not a plane. But I think that makes sense, right? All these are, it's just the array of the points. We used we used Matlab to generate them, but that's not really a really important thing. All we did is we're like, okay, yeah, pick 1, 2, and 3. We know this is an arc, this is a straight line. Give us a list of points, and that was just copy and pasted over here. So that's how that works. So now back to legs. Nope, legs demo. Sorry. Here we go. Legs. Current position is where I am in this array, right? So it's, oh, okay, now I'm here. It's not my zeta. Remember, zeta is what's actually tracking where my robot is. Again, sample time, initializing the turret because Guardian has a turret, and we're initializing it to 0 because we don't want it to rotate when we start up. And then append 6 legs, and you can see here we have I+1 and self.dh. So what this is passing, and here's our, I'm gonna try to get fancy with this. Hopefully this is not a nightmare. So if I go down to legs, okay, here's my leg class. You can see it takes in an index. This is just which leg it is. So it's 1, 2, 3, 4, 5, 6. And you can see that's what's being passed here, the I+1, right? It's 0 plus 1, so 1, 2, 3, 4, 5, 6. DH parameters as well, so that gets passed in. Every leg is exactly the same, so luckily we can just pass all of them one type. And then this takes in a path by default. It's by default, this is just the stationary position, which is what we want, right? When Guardian turns on, we just want it to be stationary. And lastly, offset. This offset is the, let's see, 0, 0. Okay, this offset had to do with adjusting the path because we were noticing we had some errors with it. I'll circle back to that once we get into the actual code of how this is getting calculated. Yeah, I believe this had to do with DH parameter stuff. So again, don't really worry about that. That's just like the modeling of the arm, and we can circle back if people are interested. But anyways, moving on, self.dx, this is delta x, so the distance each step walks me, and you can see that's just the difference between one forward path and the next, or rather one point to the next in my forward path. So that's where my dx is. And then my d phi similarly is my delta phi, so how much I rotate angularly when I go from here to here. That's all this, that's calculating. And that's it. We have a Guardian object. It's initialized. It has 6 legs. Each leg has the DH parameters. So in other words, it's modeled correctly mathematically. And we have assigned all of the legs by default, the stationary position, and we've defined what our step and rotational increments are every time we move.
Quick question.
Yes, I was going to pause. Perfect.
Yeah. I So I noticed that you assign self dot current position to the
Yes.
guardian class, and you mentioned that that's the position within the leg path
Yes.
array. So
Hmm.
why is that a variable that's assigned to the guardian itself as opposed to the legs? Because each leg would have a different current position depending on
Right. So
time.
remember how I mentioned that what we're doing is we're delaying this path.
Uh-huh.
So the way I mean, obviously there's, it's programming. There's a million different ways to do this. The way that
Yeah.
made sense in my head is I actually delay the array when I give it to the leg. So
Okay.
Guardian says, okay, all of my legs are at position 0 right now, but each individual leg has a different interpretation of what position 0 is because I delay my path
Right.
when I
Okay.
assign it to my leg. Um, Again, that's just how it made sense in my head. You can very easily, yeah, you could just, you know, have each leg have a position. This is what worked in my head.
No, that makes sense. So there's theoretically one of the legs is like the master that is on that
Yes.
actual position, and then the other ones are
Um,
offset by some amount.
Leg one yes, leg one is my master, if yeah, if
Okay.
you want to call it that. And then all the other ones are delayed. So yeah.
Okay. Yeah, sounds good.
Anything else on the inits? I guess just really quickly for leg. Leg is very similar. All these this is all just DH parameter modeling stuff. So I mean, don't worry too much about the math if you don't understand it. All I'm doing is I'm parsing my DH parameters matrix, which is, remember, like I said, it's just a big fancy way to model arms in math. So
Yeah.
I'm just parsing it, and then self dot offset is just, same thing. I'm just doing all this initializing my variables for my class, and then you can see self dot path. I'm copying path. Path length is just the length of the path. Set home is just I'm having a home position saved separately, independently from this. Um, Self dot theta. So this theta is the positions of each of my legs. So my leg looks like this, right? I have um, one rotation this way, up and down, right? I have one rotation this way, and I have one rotation this way. So this theta, oh, I'm sorry, where did it go? This theta is just what these three values are, right? So it's theta 1, theta 2, theta 3.
Yeah, I was gonna mention this earlier. I forgot. Some of us, including myself, are in kinematics of robotics right now. So
Mm-hmm.
me and Salim, who's one of the mechanical leads, are probably going to be handling the actual like
Yeah,
DH stuff.
for
Yeah,
sure.
but it's good for you guys to know about. It's yeah, just basically tells you how the robot's set up, how the geometry of it is set up.
Yeah, it's really cool math. It's actually not complicated math. It's just one of those things where it's like the concept is hard to grasp, and then as soon as it clicks, you're like, "Wow, this is so useful. Why didn't they teach me this in first grade?" So I'll be happy to circle back to that if anyone wants, but just for the interest of time, we'll keep moving. And then it also self dot simulation. All this is it's a 4x3 matrix where um, each row of the matrix is the global position of this node, and this node. And the reason I have that is I have a 3D simulation of the robot, and when I'm drawing it, it's convenient to just be like, oh, hey, connect a line from here to here to here. That's the only reason why this exists, and this gets updated as the leg moves. Self dot. It also we call set self dot reset position. All this is doing is set my position to 0 and update my simulation. It's really basic. But yeah, so we have both objects initialized now. Any questions on that now that we've fully gone over initializations? Cool. Now really quickly, just going over all the classes. So Guardian has reset legs, set turret throttle. These are, pretty self-explanatory in what the names say. Obviously, I'll go in and like tell you how the code works, but bear with me. So next position, move to, rotate, calculate rotate trajectory, calculate move trajectory, and I believe that's it. Yeah, that's it for Guardian. Legs has change path, next position, reset position, update simulation, inverse kinematics, which is this is where all the fancy DH math happens. And that's it, right? It's honestly fairly simple in terms of like code structure. And like I said, path is just, I have my simulation class, which is kind of irrelevant to this from terms of like a controls perspective. And then it's just all helper functions. And then my, two path definitions. Here you can see it's reflect, delay, translate, rotate, and path jump, which is just path jump. You take in 2 points. Let's say if in like an X, Y, Z space, I say, hey, I want to go from here to here, and I want you to jump up while you make it. So it generates this path for you of like, go straight up, move over, come straight down. That's all that class or all that function does. But that's essentially it. That's everything that makes Guardian move. Now let's go ahead and actually jump into how this control stuff works. So from a high level, we run our legs demo script. This is, like I said, this is just a simple command prompt or command input thing that I came up with. Let's say we type in move, right? Move to, we give it an XY position. Reset after is essentially after the Guardian moves, you have the option, and this is just arbitrary. I decided to give you the option. If you don't want that option, you don't have to, where the legs reset to the home position after the move. So this is just a Boolean, whether that's true or false. And then simulate is a Boolean, whether or not we are simulating the thing or if Guardian itself is moving. The reason why that's important is if any of you guys have done like SSH work, to work on a Pi, you can't get graphics back. So it yells at you if you try to simulate something when you're SSH'd in. That's why this is a separate option. Kind of like a nitpick detail, not super important, but that's why that exists. But anyways, let's say we're moving to XY and we've decided we are going to reset our legs after. What does that do? That takes us down into our long switch statement. And it calls my function guardian.calculate move trajectory. And if we're not simulating, it will move to that trajectory. If we are simulating, then it will not move and it will make a simulation instead. So now let's go to our move in Guardian. So move to will calculate I'm sorry, I misspoke. Let me clarify something. If we are simulating, we call move trajectory and simulate. If we are not simulating, we call move to, because move to already calculates. Sorry, that's on me. It's not really, it's not really a big deal. Just how I structured my code. Sorry about that. But anyways, so we're going to calculate our move trajectory, and then you can see for I in range self.total path length, we are going to wait for our sample time, move to the next position. Wait for our sample time, move to the next position. And you can see that's basically how Guardian moves. Next position is very straightforward. We have these vowels. This is just my way of making sure everything's working correctly. I'm checking if any of these change from 0 to a negative number. And if if the function returned a negative number, it gets updated in here, it gets flagged in here, and I know something's wrong. That's all this is keeping track of. There's 6 because I have 6 legs. So what I do is for next position, I in range 3. The reason I'm doing this is I wanted to move 2 legs at a time because I figured it would be more stable that way. So what actually happens is you get this leg and this leg move in sync, this and this leg move, this leg and this leg move. And that's just so that I don't have like 6 independent move commands or 6 independent move loops. Not really a big deal, just how I did it. And you can see it kind of simplifies my code since I can do like 3 times I and then I for the other ones. And that lets me do 2 legs at the same time. And so this is pretty straightforward. 90 minus self.legs.theta is what's being written to my servo. So self.legs, remember I said legs has a theta. That's just with these positions. So all this is doing is it's saying, hey, servo X or servo 1 is going to be written as 90 minus that. This 90 is just a mathematical thing. It's just how I modeled it. We realized we needed a 90-degree offset. It's not really a like super specific thing besides that. It's just we figured that out in testing. But the main idea is we're just writing our servos what the theta is. This is just, like I said, it's error checking. So if anything is -1, it's flagged here. Then we know, something's up. And if it's not -1, then we say, okay, update my zeta, my angle, and my XY positions. Any questions on this? I know I'm not like going super in detail, but this code is honestly fairly straightforward. No, if you have the understanding of like what it's trying to do. Otherwise, yeah, I can understand why it's intimidating. But any questions on this next position real quick? Cool. Yeah, so back down to here, we basically have completed our move to. The only thing we have left is calculate trajectory. But say someone wrote this function for you, that's literally how Guardian works. It's just calculate the trajectory, wait X amount of time, update all my servos, wait, sample time, update all my servos, and that's how Guardian moves. Now down to calculate move trajectory. So this is where all the real fun stuff happens. So the first thing we're going to do is we're going to define prep path 1, rotation path, prep path 2, linear path. And the reason we do this, so this is my preparation path, right? You don't want your leg to just magically snap to your first position that you want it to go to. All this is doing is prep path is going to allow me to smoothly transition my leg to a ready position before I start walking. Hopefully that makes sense. Essentially, it's like if my leg is, this got really cluttered. Let's see if I can just undo stuff real quick. Okay. Let's say my leg is in like this position, and I need it to be here when I start walking. I don't want it to just jump here, right? Really aggressively. That's not going to be nice. So all this prep 1 and prep 2 is it makes sure that I can, so from my stationary position, I'm ready to rotate. From the end of my rotation, I'm ready to move. That's all these preps are doing. But you can see it's just 6 arrays. Each one is going to become our path that the leg follows. So first up to rotate, you can see my phi. This is what I take it, or sorry, I skipped a step here. So X and Y is what we're taking from move trajectory, right? Because we're saying I want you to move from this position to move this position. The way Guardian does that, and again, this is where you kind of have the freedom of how you want to control, how you want your robot to behave. In my case, I said, if we're facing this way, I want you to rotate and then walk in a straight line till you're here, and then you're good to go. And that, that accomplishes what I want Guardian to do. Obviously, if your robot's different, you're like, well, actually, I need to go here and I need it to then face a direction. Then, you add in another rotation or you add another move. You can do all that kind of stuff. But this is just for the sake of Guardian, this is what we needed to do. So you can see it's first, it's going to figure out how much it rotates by. So just arctan of y minus my current y, x minus my current y. And then it takes phi and it unwraps it. If you're familiar with Matlab, you know what that does. You're essentially making sure that it's not past 180 or 180 degrees. Self.d phi. Remember, we calculated this already up here. This is just a repeat calculation, just in case you passed it, you overrode something, right? You were like, hey, actually, I changed my mind. You're going to follow this specific path now. This is just making sure that our simulation is still correct. And so it's just recalculating that. Next up, n. This is just going to calculate. It's going to seal the ratio between how much we need to rotate and how much we rotate by each step. So all this is really doing is telling you how many steps we have to rotate. Steps meaning individual, position steps in this array of position or array of path. Obviously, if n is not equal to 0, we're going to calculate all our rotation stuff. So if n is greater than 0, we're going to copy our counterclockwise rotation. Else, if n is that would make it less than 0. We're going to copy our rotation and we're going to reflect it so that we get our clockwise path, right? Because remember I said we defined our counterclockwise rotation path. So all this is doing is if n is less than 0, meaning we want to rotate this direction, it's going to reflect my counterclockwise mathematically so that I have my clockwise rotation. And it's also going to negate my self.d phi because remember I'm rotating the other direction now. Also, I'm going to make n negative so that when I do a for loop, it doesn't get mad at me. Next up, after that is set up, we're going to do for I in range 6 because we have 6 legs. We're going to take a delayed path. So this is where the delaying happens. We're going to take in my rotation path, which is what I just defined up here, and we're going to delay it by this using this delay array. So this is where, remember I said, oh, I'll get back to that because it won't really make sense unless I explain how you're walking. Where did it go? Yeah, so here's my delays, 0, 16, 32, 0, 16, 32. That's based off the fact that we have, I believe, I don't remember how many, however many it is, I think it might be 32. Or no, that doesn't work. Whatever it is, it's just defining that leg 1 and, leg 1 and 4 have no delay. Legs 2 and 5 are delayed by 16, legs 3 and 6 are delayed by 32. That's just based off of these arrays and the fact that that's how we decided Guardian was going to walk, based off that like delayed
So
walking gait pattern.
there's probably like 48 point then.
Yeah,
Yeah, divided.
that sounds right.
Yeah, because each offset is 16 steps away.
Yep, that
yeah.
checks out. I just didn't feel like doing the math, but yeah, no, that checks out. Okay, so yeah, that's that. We're going to delay it. Next, we're going to take path length, which is just, calculating how long this is. We're going to take a temporary path, which is essentially we're going to take this, we're going to take delayed path, and we're going to take the first row of it. I'll circle back to this. Just follow me for 1 sec. I'll circle back to this, I promise. So we're going to take the first row of my delayed path, and then based on that, I'm going to keep adding in down the path. Let me move this over here. I'm going to keep adding in consecutive, elements of this overarching row to, sorry, that's forward. Here's rotation. Overarching row to my, to my temp path. And then if I reach the bottom, that's what this is here for, the J+1 mod path length. I'm going to go back to the top. And that completes what, and then the last thing I'm doing, I'm saying rotation path I equals temp path. Rotation path I remember is just all the leg paths. So a little bit more detail of what this is exactly doing. So I am taking, here it is. So I'm taking rotation path, I'm taking this, I am saying I either need to flip it or I don't have to flip it, depending if I'm going clockwise or counterclockwise, right? That checks out if you're thinking about it, looking at this thing. And then I'm saying, okay, next I'm going to delay it by however much I need to delay it. So this is going to make sure that this leg, because remember I said this is the rotation, all of them have the same path, but they start at different positions. I'm going to make sure I have the correct delayed path, which means that in the case of leg 0, remember there's no delay. So leg 0 is just, or leg 1, excuse me, is just going to get this array as is, right? It's just going to get a copy of this array because I'm not delaying it. Delays I was 0, remember up here, is 0. So it's not delayed. This is the path that my leg 1 is going to follow. And then I take the length of that path. I'm going to take the first element of that array, and then for as many times as I need to make sure I rotate by the amount that n is telling me to, I'm going to keep appending on consecutive rows of this overall path. If I reach the bottom, that's what the mod is for. Just start over until I make sure that I rotate as much as I need to. To give another example of one that is delayed, let's say we're going to do leg 2. So now we're going to do this one. We know that this is delayed by 16. So I'm going to copy over this thing, the whole thing. I'm going to delay it by 16, which means the first 16 elements are going to move to the end. And so I don't feel like counting, but let's say this is my 16th element. This is now element 0. That's what gets copied first. And then the same thing repeats of I keep adding on consecutive. And if I run out, start over. Right? Does that make sense? That is how I calculate the path that my rotation follows. And then self.movesteps, all this is doing, this is a big array that keeps track of how many move points are in each subset of the move. I know there's a confusing way to say it, but if you look back at this, right, this overall thing is one move command, but these are like sub moves, if you will. So all this self.movesteps is doing is it keeps track of like my delay, or sorry, my prep is this X long, my rotation is Y long, my second prep is Z, et cetera, et cetera. That's what this is doing. I'm going to really quickly skip the prep and go to the move, the linear move, because it's exactly the same. Linear move is right here. Same thing. I'm going to take S. I'm going to figure out how much I need to move. So, square root of current or target X minus current X, target Y minus current Y, calculate how much I need to move, update my move steps. Same thing, just say, okay, to make a linear move, that's how many steps I have. And then once again, if my N is not equal to 0, for I in range 6, delay the path, figure out how long the path is, take the first element of the path, and then for however long I need to add on, consecutive rows of my path. Cool? Make sense? So the only tricky thing with the linear move, which this is just inherent to the way that legged robotics works. So remember how I said every single one of these legs follows the same path? The problem is this leg has it in this plane, even though technically the circle is the same. This leg has it in this plane. That means this leg is not going to do the same motion like you as an inertial observer will not see this leg and this leg do the same thing, right? Because this leg up here, leg 1, is going to go here and to here, right? If you do the like total sweep of motion, this leg is going to go here to here. You can see these two are not the same. Even though the end of the leg is following the same, semicircle path, these two legs are not doing the same move, right? Does that make sense? So these last three, these last three lines is what makes sure I take this general rotation and say, okay, well, make sure it's rotated mathematically to be in this, be in something this leg can understand. And so the first thing we're doing is we're checking, is it leg 0 or is it leg 1 or 6? And that's because remember, indexing starts at 0. So if it's leg 1 or 6, what we're going to do is we're going to translate the path. And what that's doing is it's taking, sorry, I'm going to double back really quickly. The way this is defined, these points, I probably should have mentioned this, I'm sorry. These are defined using the body unit vectors. So remember how I said this is X, this is Y. So when we define this path, it's defined using these unit vectors. But this leg actually has unit vectors like this. And that's unfortunately because of the kinematics course. So if that doesn't make sense, I'm sorry, just accept it. That's how the modeling works of it. But you can already see that there's a problem here. I have to say, well, hey, I defined my path in this frame of reference. How do I get it in this frame of reference? So the first thing I'm going to do is I'm going to translate it. I'm going to say, well, the origin isn't actually 0, 0. My origin is however far this is, right? That's what I need to translate by, because you can see in path, this is based on 0 being, the center of my semicircle. And the reason that is because that makes Matlab easier when we're generating these paths. But in the case of this leg, since the origin is here, so we're going to translate the origin. That's all this is doing. If it's 0 or 5, so if it's leg 1 or 6, we're going to increase by X. And either, you can see it here, we're going to 0, 5, we're going to translate by we're going to translate the path by the offset. This is where I guess my shitty naming convention is biting me in the ass a bit. But so remember this offset up here that I was like, I can't really explain this till we get into it. So this offset is based off of the physical geometry of Guardian. The 0.08 is this 0.08 up to where this leg is, and this minus 0.02 is this is all in meters, by the way, hence why the numbers are so small, is the distance this way. So this offset, path offset, is 0.08 up and minus 0.2 over. And so that's what will tell me, basically using these two numbers, I will translate the origin of this path from in the middle to the origin is here now. I realized that I just like circled back a million times. I'm really sorry. I'm gonna take a second to pause and make sure everything makes sense because I know this is rough. But at least from like a big picture perspective, do you kind of get what I'm trying to do here? I'm essentially saying I have a path, I'm going to move it, and I know that since my robot is, you know, perfectly symmetrical, I only need to really define one of these offsets, and then I can just use them repeatedly. So now back down to my move command. So yeah, if I is 0 or I is 5, meaning leg 1 or 6, we're going to translate by that amount. So we're going to move it. If I is 2 or I is 3, that means if it's my hind legs, if it's this leg or this leg, we're going to do the negative version of that. We're going to go back. Cool, makes sense. Pretty straightforward there. Now that that's kind of explained. And then lastly, we're going to rotate them because remember I said this has to be rotated because this frame of reference is not parallel to this one. So we're just going to rotate this to make sure it's in the correct plane. But after that, so the core of this is the same as the rotation. The only fucky thing is the fact that since this is not a curved path, it's a linear, you know, it's a planar one, we have to rotate our plane. But once that's said and done, this again gets added to my linear paths up here, and that's done. Cool. So now we have rotation and we have our movement. All we have to do left is figure out how we prepare for the rotation, how we prepare for the movement. The code for this is identical for both preps, so I'm only going to go over one of them. And in fact, remember how I said you have the option to reset after? The code for the reset is also the same. The only difference is instead of assigning a, you know, what does Python call these? Assigning a dictionary. Instead of assigning a dictionary for the path beforehand, I'm just going to append it to the end because we don't always reset. So it's just a waste to generate a function we might not use. But so let's go over one of the preps. So we're going to do the prep for the rotation, but like I said, it's the same code. It's literally just copy and pasted, and maybe like I tweaked like a couple things. But I honestly don't think so. I'm willing to bet I didn't. So if move steps 1 is greater than 0, all this is checking is, remember, move steps is the keeping track of how many in each of these there are. If I'm not rotating, I don't need to prepare for rotation. So that's all this is saying is if I do have to prepare for rotation, yeah, let me do this. Hopefully this helps. I'm going to define a temporary path. I'm going to define 6 of them, 1 for each leg. And the initial path is going to be the current position. So you can see it's taking the current position of the leg. This is unfortunately disgusting to look at, but it's self.leg. So it's guardian.legs, which is my array of 6 legs objects. Take the first leg, second leg, etc. Take its path, and then take the current position of that and take the first row of the array. Because remember, this is a, you know, a big, long array. So I'm taking, basically fancy way of saying take the current position, current XYZ point you are currently at. Unfortunately, it looks like this because it's math and I kind of how my code is structured. But that's all I'm doing is I'm taking the first position that my thing is currently at, and I'm taking the remember I calculated my rotation first. I'm taking the first position that my rotation is at, and I'm passing that to my jump function in path, which if you remember, I said you give it a start position and end position, and all it does is it calculates a square move from start to end. So technically my work is done for me here because I have my path. I said, hey, this is where I'm currently at. This is where I want to end up. Do it 6 times for each leg. Then the only thing I'm going to add to this is, since not every leg has the same amount of prep, we have to address that, right? So for example, the move and the rotation is easy because for me as Guardian to move a meter forward, all 6 of my legs have to do the same amount of motion, right? It's not like one leg moves more than the other. Same for rotation. If I'm rotating by 90 degrees, all of my legs do the same amount of rotation. But if I'm preparing to move, one of my legs might already be good, right? So I can't just blanket statement say, okay, hey, all of my legs are going to do n amount of move points. So that's where the rest of this code comes in. All this is going to do, and I'll kind of go through it as well, but just to high level, all this is going to do is it's going to figure out how much each needs to move. It's going to take the largest number, it's going to make a for loop with the largest number, and then in that for loop, as soon as one of my or not sub, wrong word. As soon as one of my legs runs out of path because it's, reached its target position, I'm just going to add on the same position it's currently at. So what that looks like in not word vomit, let's say, this is my current position, right? Where I want to end up is this leg doesn't move. This leg ends up here. This leg ends up here. This leg doesn't move. This leg ends up here. This leg ends up here. Completely arbitrary, but just for the sake of, example, follow me. This one doesn't have to move at all, right? So this has 0. Let's say this move takes me 16. This move takes me 8. And then since this is reflected, this would also be 0. This would also be 16. This would also be 8. I'm going to say, okay, for I in range 16, because that's my largest number, we're going to add on each of the path, just like how we did here, where I said we used the mod function, right? To say, as soon as you reach the end of the path, go back to the start of the path and keep copying individual data points till you get the path that you want. We're going to do the similar thing, but now instead of using mod, as soon as we reach the end of my path, I'm just going to copy the position I'm currently at. So 8 steps in, this leg 1 is going to have a bunch of an 8 element long array of the same exact point. This is going to have 8 unique points. This is going to have 8 unique points. But then I have to go to 16, right? So for the next 8 points, 0 also has identical points. 8 has identical points of the last point, and 16 has all 16 unique points because this one, remember, takes 16 steps to get prepared. So again, any questions on this? Hopefully the word vomit wasn't too bad. In theory, basic idea is, not every leg takes the same amount of time to prepare. So if my leg is done preparing, stay at the same position. And the way I say that is move to the same point you're already at. So technically you don't move because remember, if I tell it to move to where it's already at, it's not going to do anything. Cool? Makes sense? So what this code is doing is it's doing essentially that. So I'm taking, that's the linear move. I'm taking, right now that I figured out what my jump paths are, I'm going to append the first position, just like I did for the move and the rotation basic. And then for I in range 3, I guess I structured this a little differently, but the idea is still the same. I in range 3, we're going to do 2 legs at a time because remember, our robot is symmetric. We're going to take the prep path and we're going to append where we're currently at. So we're going to append to prep path, which is, remember, just these overarching matrices or arrays. We're going to add my temporary path, which is here, the one that I said we just calculated with jump. And then for my I+3 leg, which is just my mirror leg, do the same thing. Then for inside this loop, we're going to say for j in range 6, if n jump I is greater than n jump I+3, remember this is where I'm checking who has the longest jump, right? Which one of these legs has the longest path? That's where I'm figuring this out. And if I have essentially surpassed my, if I've surpassed where my path length is, I'm going to take my last position and I'm just going to keep copying it on. And you can see it's kind of complicated, so I don't want to like go through this also for the interest of time. But essentially, that's all this is doing is I'm saying take the ith element, but in this case, since I can't just say I have to make this complicated statement where I'm saying, oh, take the shape of this matrix and then take the 0th element of that and subtract 1. And so don't worry too much about that. Obviously, feel free to look at it, and I'll be happy to answer questions, but I don't want to confuse people any more than I realistically probably have already tonight. But essentially, all this is doing is describing what I said it's doing. It's just copying on the end of the path. Then we, like I said, we do our linear move, then we prepare for our linear move exactly the same way, and then we reset after in exactly the same way, except our end position is our reset position. And that's it. Then we combine all of the paths, because right, I have all of them as separate arrays. All I'm going to do is combine them all into one long path, and I'm going to leave this calculate trajectory long bullshit function, go back to my nice, cute move to function and say, okay, now that that nightmare is over, move, please. And that is quite literally how Guardian works. The only part that I didn't really talk about is how do I say, okay, well, I want to go from this point to this point, but that's like XYZ coordinates, right? What angle does my servo need to be at? Right? Because I didn't really talk about that. Well, that's where inverse kinematics comes in, right? That's the complicated fucky math that I'm telling you about. That's you'll learn about if you take the 163 series. Or if you don't, obviously feel free to ask questions or reach out to me. I'll be happy to explain anything about it. But so if you go into my legs object, not my Guardian class, where is it? So my legs class, I have a function in here called inverse kinematics. So this is where all of the disgusting math happens that goes from XYZ position to what 3 thetas, because remember we have one rotation here, and then one rotation here for my leg, right? What 3 thetas get me here? What 3 thetas make this tip go to this XYZ position? All of that disgusting math happens in here. I did all of this by hand calcs and then converted it from hand calcs to Python code. So I will not walk you through that nightmare, but if you're interested or feel like learning more, feel free to reach out. I will happily answer, but just not here. And the way this works is, remember how I said each leg gets assigned a path? Well, as soon as you assign a leg a path, I'm going to go ahead and calculate all of them. I'm going to take that whole matrix of the path that I just passed to you, this whole thing, and obviously modified however I need it to be modified, whether I'm moving or rotating, blah, blah, blah. I'm going to pass it to inverse kinematics. I'm going to have inverse kinematics spit out a long matrix of, instead of XYZ, and instead of having, XYZ, however many points I have to move, I'm going to have theta 1, theta 2, theta 3 corresponding to my 3 servos, however many points I need to move. And then, so that exists now, because as soon as you call change path, I am saying, okay, well, give me my inverse kinematics. And I no longer care. That's it. That's done. And then next position just says, okay, well, I know what my next 3 thetas are. Just update my servo so that I have the next 3 thetas. And that is how Guardian works. That is actually all of the movement code for Guardian. I have covered everything that I worked on last year in the course of an hour. And I know that's a nightmare. So please feel free to ask me anything now, obviously. Or if something comes up after you look through my code and you're like, John, you're a fucking idiot. Why did you program this way? Feel free to reach out and I'll be happy to get back to you when I get the chance. But yeah, that is everything Guardian related. I will stop sharing my screen temporarily while I get Visual Studio open, because I think I have to do a git pull real quick. But in the meantime, any questions on anything?
That was amazing, John. Thank you. That was
No
a
problem.
wild ride.
Yeah,
we
I'm
went
sorry.
down the rabbit hole, and then we went down the rabbit holes inside the rabbit holes.
Yeah.
So that was really something.
But yeah,
Yeah, thank you so
that's how
much.
everything works. The only thing that this doesn't have, obviously, is like feedback loops, but all of the framework is there, right? We have a sampling time set up, we have a move command set up. So the only thing left would be set up a command for, well, where am I, right? I said move, but where am I? And then you basically have your feedback there,
Yeah, yeah.
whatever that sensor might be. So um,
Which
yeah,
was originally a plan for this robot. I'll remind you guys. There was going to be a sensor outside feedback of the link figurine, which would get converted into a command to move to a certain position where the figurine is at. Remember, just didn't all get connected together, but yeah, that was the original plan. That will probably end up being some kind of plan for this robot. Yeah.
let's see if I can do this. Start without debugging. Please work.
Oh, is this the simulation?
It is indeed. Am I getting an error
I got the
here?
simulation to run on my computer. I felt proud.
Unresolved import path. Interesting. Why are you? Oh, I don't know why it's angry with me. Um, oh, oh God, Visual Studio is so annoying sometimes. Start without debugging, please. Or not. Okay, I guess we're gonna do this in debug mode. Hopefully it works. Okay. Cool. So obviously I don't have a Guardian on my computer. My computer is not a Guardian, so all my servo library stuff is disabled. But so here's my thing. I'm gonna say move to, we'll do 0.75 meters, 0.25 meters, reset after, and simulate. And so we're gonna move to that position. So you can see, here's a better understanding of how Guardian walks. So you can see this is, first we're gonna rotate. So we're gonna do the rotation path. That's what this is doing, right? And you can see that now we're gonna prepare for our move function. And then, so you can see they're moving in pairs, like I mentioned. And now we're gonna start doing our move path, which is, here's your semicircle right here. And I'm walking. That's Guardian. This is exactly what the servos do. There's no code different between how this is calculated and how the actual Guardian is calculated. The only difference being, instead of writing to servos, I'm writing to a XYZ position. All these dots are just linked to one another. And remember how I said I had a, let's see if I can, oh, my computer does not like that. Oops. But you can see, remember I showed you guys the legs class has an array called simulation. These are all these points that you saw there, like the dots. And so I'm just linking them in my simulation class, which is in path, which again, I'm not going to go over, but I mean, this code is actually fairly straightforward, and Matplotlib has really great documentation if you're interested. But yeah, ta-da, Guardian. Cool. And now I'm officially done. So yeah, any questions at all, or otherwise you can leave me the rambling old man.
I had one question. I might have
What's
missed
up?
it. I saw like some sleep like function calls there, but like just in general, like how is it like how does this work in like real time? Because I didn't really understand like how I guess like at the rate at which like the like move commands are.
Yeah, okay. So these ones here in this demo loop, right? Remember I said these are only for how it moves. So that's why these numbers are so big, right? This is like sleep for a second, because I'm saying like, oh, rotate and then wait a second, and then rotate the other way. This is just like, how I decided I want Guardian to move. But in terms of like an actual controls perspective, that's where our sampling time comes in, TS, right? And so the way you would do this is if you wanted feedback, for example, in your move to, this would be different. Actually, let me pull up my capstone code real quickly. Let's see if I can. I'm gonna have to restart this because I know it doesn't like me when I do it otherwise.
Wait, what was your capstone project?
My capstone was called Spasm. It was a pool Roomba, so it skimmed the surface of your pool.
Oh, that's
interesting.
cool.
Wow, oh, there it is. So this code actually has sensor feedback. Obviously we didn't build it because we did it last year where we were still in like primetime COVID stuff. But I actually made fake digital, I guess, virtual ultrasonic sensors on the corners. Let's see if I can, excuse me for a sec. Let me pull up my report so you can see what it looks like. I promise this won't be long if Duo will let me log in. Spasm final report. So yeah, this is our capstone. It's essentially, like I said, it's a robot that floats on top of your pool and skims all your leaves for you. So yeah, I guess this is probably the best picture for it. We have ultrasonic sensors on each corner, and we're using that as feedback to make sure I don't hit any walls. So this code is actually a little bit more robust because of that. I actually have multi-threading for this simulation because it was running better. So and I'm like, I also needed a separate thread to simulate my ultrasonic sensor because it would have been too laggy if I was reading sensor data after I moved. It was taking too long. So hence why multi-threading is happening here. But essentially the idea is the same where, where's my run loop? I'm going to move, let's see. So I have two threads here, right? I have robot thread, sensor thread. The sensor thread, like I said, is just taking in my ultrasonic reading, and it's using a particle filter, which is essentially a particle. Okay, what a particle filter does is real robots don't know where they are, right? When you tell them, hey, you're at XYZ, they're like, cool, but am I really? So what a particle filter does is it uses sensors to generate a bunch of probable locations and then narrow down that probability till you figure out where you are. You'll actually see that when I run the simulation for this. You'll see a bunch of guesses of where the robot thinks it is, and it gets, tuned eventually. But so that simulation is happening in another thread. I have my movement happening in another thread. And in my move command here in my controls, I'm actually checking, how I'm doing basically, and I'm using that to adjust my movement a bit. So that's if you want like a more practical, explanation, that's kind of how you'd want to do it. You want to interlace your sensor readings with your move commands, like I mentioned. And in the case of Guardian, the simplest way to do that is in my move command, which is here. I'd have you sleep for my sampling time, move to my next position, and then check my sensors, and then repeat. That was how I would do that. And the reason why so I know you said like, oh, well, why are you using sleep? Basically, if you've taken, there's a digital controls class, I think it's 172A or B, I don't remember. I should because it was last quarter and I'm not that old. But essentially, you'll learn that you can't just have infinite sample time, right? Or I guess zero sampling time. You can't have infinitely many samples because you'll have so much noise that it's basically useless. So what your sampling time is doing is you're saying, well, I know realistically I'm running this off a Raspberry Pi. My Raspberry Pi isn't some kind of, liquid cooled supercomputer. It has physical limitations to how quickly it can make commands go. So if I artificially throttle it, and in our case, Guardian moves so slowly that 0.01 seconds, I guess, is what it has to be because of how this function is called. 0.01 seconds or 10 milliseconds is perfectly fine sampling time for us. And so you can kind of play with that. It's obviously I have the sampling time way smaller in this case. I think it might be like 1 millisecond, maybe even 0.1. But in this case, I need it because if I hopefully this one works. You'll see this is like updating real time, reading off of my 4 sensors, and then, you know, updating my move commands as I do that. So in this case, my sampling time's, you know, way smaller. It's really fun to watch, so I'll do it again. You can see all these white dots are the guesses of where the robot thinks it is, and then as it's taking in sensor feedback, it goes, oh wait, well this is the only probable location that I can be, and it still jitters because these are all still estimations. Right? You can see them kind of jittering about it. But yeah, essentially the idea is the same. Is you, in between your move commands, you take in your sensor data, and if you want to get like really fancy and apply like PID control or something to it, you would do all that stuff in between your move steps, and that would be used to adjust your path. Right? Does that make sense? Really long explanation to your question. I'm sorry, but I hopefully that helped.
Oh yeah, that was great. Thank you.
Anything else? We can just stare at Spasm, just move around for a bit if you like.
It's so cute. So good.
This uses the same code, by the way. So it's X, Y, and Theta. So it uses the same zeta vector. I use the same path translation stuff. I use the same calculate trajectory. All that stuff is the same. And that's not to say like my way is the correct way to do it. That's just to say that like this isn't only for Guardian. You know, this code works exactly the same. You can see I've structured my code a little differently here, but like get arc, get line, these are the same thing as what my move trajectories would do. You see Zeta is still here, DS is still here. I had to get acceleration in my case, but that's because I was using like proper feedback controls. So, but yeah, that's yeah, Python non-ROS robot control in a nutshell. At least my understanding of it. Obviously, there's a million different ways to do this.
Thank you. Very informative.
Yeah, no problem.
I feel like I got to follow up later and just read the whole code over again to confirm everything. But
yeah, I know, of course.
Just a lot. So
I'll ask you one question, John.
Yes.
Why are you allergic to code comments?
Why am I allergic to code comments? The reason why I'm allergic to code comments is you'll see I'm not as bad in this in my code for Capstone, but I was so exhausted for this stuff because this was like I was doing Capstone while writing Guardian controls code, and I was like copying pasting from like one to another. So yeah, I'm a terrible human being for not commenting this shit. I can probably do that if you like. It shouldn't take me a long time. But yes, I am a terrible human being. Also, I figured incorrectly, but I figured that I would be the only one to ever look at look at this after we were done with Guardian. So I was like, it's okay.
No, I mean this is so
me.
useful. Like this is exactly the code base that we need, you know, to figure out how we're doing this new robot. So having this is actually insanely useful. Yeah, just like if you could put just really brief reminders of to tie it back to the stuff you said in here, like we'll have this video to go over for the more specific things, but like maybe just putting it in sections of like what's going on in each section.
Yeah. No, I completely agree. That's on me. But yeah, I mean, I recommend you guys, I mean, don't try to adapt Guardian code. I would strongly advise against that. I would say, or in the sense that don't like copy my code from Guardian and then change variables. And that's not like because I'm like, oh, don't touch my code, proprietary. No, I don't give a shit about that. What I mean is like your life will probably be way easier if you can start from scratch. Say, okay, I have a class that is my robot. My robot has X, Y, and Z subclasses. You know, like your basic CS31 stuff and 32. It will help you have a way more intuitive feel for what you're actually doing when you write up this controls code. At least I found that was the case for me. So that would be my 2 cents on it. But yeah, that's basically it. This should be on my Git. I believe it's public. If it's not, I will make it public.
Yeah, we have access to it.
Yeah, it's public. So.
Okay. Is my capstone as well?
It might be, but I don't know. I haven't looked at it.
Okay.
Yeah, it is.
Yeah, it is. Okay, cool. Yeah, feel
Yeah.
free to use that as well.
Sure.
If that's helpful. Oh yeah, it is public. Yeah, feel free to take a look at that as well. Yeah, there's a lot of stuff that didn't get done, but I mean, like we didn't buy an LCD screen, so there was no point. But yeah,
Wild. Yeah, thank you.
yeah, no, my pleasure. Again, feel free to reach out for anything. Even if it's like, John, I don't feel like doing inverse kinematics. Can you help me? I'll try to help
We'll
out.
be okay. Yeah, we'll
Or
we'll have
pester
an
Gabe
interesting.
about it.
Yeah, Gabe will help me too. We're making our own robotic arm in kinematics robotics with Gabe
Oh
on the
yeah,
team again. And we've
yep.
nicknamed
The
ourselves
soup stirring one, right?
the soup stirring one. Yeah, we've nicknamed ourselves the bench warmers because your team obviously was the dream team, the
Oh
A
no,
team, etc.
we were the Boomer Squad. That was our name. We called ourselves the Boomer Squad.
Yeah. So our new team, we're not quite the superheroes of you guys, but
Oh no,
just
don't
gonna
say
try
that.
and make our little soup robot. We're gonna make it work.
Y'all are great. Y'all got this. Both for X1 and obviously that stuff. Yeah, feel free to reach out for anything, y'all. And like I said, I'll try to help out. And if I don't know the answer, I'll try to find someone who does, especially for like, if for some reason you're like, hey, I really want to know how, this OpenCV stuff you guys worked on did. I could not tell you. I could tell you like really, really broadly how that works. And I
Yeah,
can tell you to like go hit up Bradley, but
Bradley, and then we have Nikhil is still leading
oh
our
yeah,
robot
cool.
team.
Oh
Yeah.
yeah. Oh yeah. So that's that. Thank you for listening to my ramblings, and this has been my TED Talk on programming with a mechanical engineer.
That's very good. All right, we have some soft applause from Rohan. Very good. Yeah. All right. Any last thoughts, or it's all good? We're a little over our usual meeting time.
Yeah, sorry about that.
No problem. All right.
Cool. Yeah. Thank you so much, John. That was great. I think again it's something I guess to go back and look at, but I think there's a lot you can learn just from the way it was structured. Especially that's my first takeaway. But I just gotta ask for the CS team. Do you guys have anything like you'd like to mention while you're just here as a team? Because I know it's always a little harder to communicate over Slack. So, or anything you want to get done this week, or
Yeah, I stole your
assignments?
guys' meeting time to have this, so you guys didn't have to actually talk to each other.
You can keep it quick. If you don't, just feel free to communicate the Slack, I guess.
I'm gonna stop the recording now.